Okay, now with the steps of the light-dependent reaction for the photosynthesis. We said that we are having integral proteins, photosystem 2, photosystem 1, and ATP phosphatases. All of those are integral proteins. So, after photosystem 2, you have some sort of electron transport protein, and we call this the electron transport chain via proteins. Electron transport proteins. And after photosystem 1, you have only one carrier protein. We call this ferredoxin. And then you have another integral protein, but let's leave this for later on. So, photosystem 2 has two parts, two on the external sides, and then something within the center of the reaction. We call this the center of the reaction. Center of the action. At the external sides, you have some sort of pigments. Those pigments are called accessory pigments. They are called accessory pigments. And within the middle, within the center of the reaction, you have chlorophyll, the main pigment of the plants. The green pigment, chlorophyll A or B. But over here, we have chlorophyll A. So this is chlorophyll A. What really happens? Let's start with the steps. When sunlight, which is a major reactant for the light-dependent reaction, strike the leaves or any part of the plant that contain chloroplast, accessory pigments would receive the sunlight energy. We call the sunlight energy photon. We call it photon. It's an energy of light. This photon will be transferred from one accessory pigment to the other. What happens here, happens there. From one accessory pigment to the other. And later on, they will start to transfer the energy to the center of the reaction. You know that chlorophyll is a molecule, and every molecule has its valence electron. What happens to the electrons when they are excited? They jump to a higher energy level. That's precisely what happens. The electrons of the chlorophyll that have been here and they receive the photons of light will be excited to a higher energy level. Now, this electron of the chlorophyll is very excited. We can never leave an excited electron. So they need to pass by some sort of integral membrane proteins put in some sort of a step down form. So they will jump from over here, lower down, till they once again back inside that thyroid membrane, inside lumen, from where they have started. But now this electron is de-energized. Why? Because every step down, an energy has been released from the electron that have been initially excited by the sunlight. So this electron is a de-energized electron. De-energized electron. And over here, the chlorophyll loads its electron. So the chlorophyll of photosystem 2 is missing one of its electron. What happens to photosystem 2? Precisely happened to photosystem 1. So the accessory pigments would absorb the sunlight and then shuttle all the amount of energy to the center of the reaction where the electron is excited to a higher energy level. Now this electron will jump over just the first electron transport protein ferredoxin, then later on this electron would combine with an integral membrane protein. We call this membrane protein NADP reductase. And from the name you would know that it works in reducing something, works in reduction. NADP reductase. So the electron over here will combine with the NADP reductase. This NADP reductase would catalyze the formation of changing NADP plus H or energized electrons 1 as well. So this molecule of chlorophyll is unstable. Why it's unstable? Because every single time when sunlight has been absorbed once again during another cycle, it's missing one of its electrons. So you need to make sure that this electron is substituted. We said that one of the major reactants used in light dependent is water. So water is already found inside the plant. Water over here is found inside the plant. When sunlight during the light dependent reaction have been absorbed, what will happen? It will excite the chlorophyll, and as well it will work on something called photolysis. It will work on something called photolysis. What's photolysis? Photolysis is the dissociation of the water molecule. The water molecule will be dissociated to its main components. You have hydrogen, you have electron, and then you have oxygen. So now you have 3 electrons over here, and you have hydrogen that have been dissociated from the water, and you have oxygen. Once again, back to the equation, you know that oxygen have been used or produced as a waste product. For the plant, it's a waste product, but for all other heterotrophs, it's the main reactant. So oxygen will be released out as a waste product. So what about this electron? This electron would go and compensate for the lost electron of photosystem 2. And what about this de-energized electron? This de-energized electron would compensate for electrons of photosystem 1. So now, back again, photosystem 2 and photosystem 1, each one of them is restoring its main electron. Photosystem 2 restored, let's write this over here. Photosystem 2 electrons is restored during photolysis. And photosystem 1 electrons is restored by photosystem 2 electrons. Okay, this is regarding restoring the electron, and now you form it the NADPH, which is a main reactant, which is the main product of light dependent. So what about ATP? Let me remind you of the general equation of light dependent. Light dependent, you are using water and you are using sunlight in order to produce oxygen, ATP, and NADPH. You use the water already. You produce the oxygen during photolysis. You produce NADPH from NADP reductase from the electron that have been extracted from photosystem 1. Now what about ATP? ATP will be produced during a process called chemoosmosis. Within this ATP phase, if you started to allow ADP plus phosphate to form, it will form an ATP, yet this requires really high amount of energy. We can speak about this later on.